Now let's take a deeper look at performance comparison between single cycle and pipeline designs. Performance is basically the time it takes to execute the application, and this time depends upon three parameters. Instruction count, the number of instructions in the application; CPI, the number of clock cycles it takes to execute one instruction; and cycle time, the length of the clock cycle. The first parameter, instruction count, is same in both designs if they are executing the same application. CPI is also same in both designs, and it's 1 in both of them. It's 1 in single cycle design because it takes one cycle to fetch, decode, and execute an instruction. And in pipeline design, even though an individual instruction takes 3 cycles, one cycle for fetch, one for decode, and one for execution, because we overlap the execution of different phases of different instruction, we see one instruction finishing execution per cycle. So that's why the CPI in pipeline design is also 1. However, it's actually slightly less than 1 in the beginning. This is because until the pipeline becomes full, we do not see any instruction finishing the execution. But in a long running application, this initial period for filling the pipelines account for very less time. So effectively, we see CPI of 1 as a whole. Finally, the cycle time is the differentiating factor between these two designs. As we saw in the last video, ideally, it can be ideally pipeline design can have 1/3 of cycle time of a single cycle design. And this is because of this, pipeline can provide 3x performance compared to single cycle design. And this performance comes because of two factors. First is we overlap the execution of different instructions, and then the cycle time is smaller. Now this overlapping is important because if we were not overlapping the execution of different instructions, each instruction will take 3 cycles to execute. And if we are reducing our cycle time by 1/3, but each instruction takes 3 times more cycle, the overall execution time will remain same. So it's the overlapping and the small cycle time that makes pipeline design to provide better performance than single cycle design. Also, this 3x performance is ideal case. And in practical design, it's actually less than ideal. And there are two factors that makes it less than ideal. One of them we have already seen in the last video is the cycle time. To get a cycle time that's 1/3 of single cycle design, we need to distribute the work among fetch, decode, and execute stage equally, which is really difficult to do. Even if we are able to do that and our cycle time is 1/3, getting a CPI of 1 is also difficult. And it's not because of this initial delay, but there are other factors that do that. Let's take a look at what these factors are. So there are these dependencies because of which there are some empty stages in the pipeline. So till now, what we have been assuming is that all the stages of the pipeline are always busy once you have filled up the pipeline. But this need not to be the case because of dependencies. There are several types of dependencies. First of all, we have data dependencies, and these occur when when the results produced by one instruction are needed as input in a different instruction. We have control dependencies, which means whether or not to execute an instructions depend upon a previous branch, whether it was taken or not. Now, if you see, these data and control dependencies are feature of applications. They are application properties. Whether or not you have a pipeline design or not, it's independent of that. Even in a single cycle design, dependencies exist. However, whether these dependencies may lead to incorrect execution or not depends upon your processor design. In a single cycle design, you do not really have any hazards. When you have pipeline, at that point, you need to make sure that you handle these dependencies properly to avoid hazards. And hazards are the situation that might lead to incorrect execution if you do not handle a dependency properly. Now, one way to avoid hazards is to pause the pipeline. That means if you detect that there might be an hazard, you stop operation in some of the stages of a pipeline. And if you do that, your CPI automatically gets lower, which results in lower performance. Let's take a let's take a look at data dependencies. So here we see a piece of code, and in this code, let's find dependencies. First of all, true data dependencies, and these are the dependencies where the data produced by one instruction is read by another instruction. So for example, I1 writes to register R1 and then I2 reads this register R1 and use it as an address. So there is true data dependencies as data is moving between these two instructions. Also, there is a dependency between I1 and I3, again because I1 is producing something that is needed by I3. Okay, let's try to find out more dependencies in this piece of code. Can you try and find some more dependencies? And a dependency is when one instruction is write to a register and the second instruction reads a register. For example, here is a dependence. I2 write to register R2 and I4 reads this register. So there is a dependence between I2 and I4. Then I3 writes to this register and I4 reads this register. So there is another data dependence. Similarly, I5 writes to R1 and I6 reads it. So this is another dependence. Also, I4 writes to R4 and then I6 reads this R4 and save this in the memory. So this is also a dependence. Okay, so what we have seen now is that some of the instructions are writing while the others are reading. So data is moving between these instructions. So there is a dependence. Now let's take this situation. I1 is writing to R1. I5 is also writing to R1. Can this be considered a dependence? According to our definition of data dependence, we do not see any data being moved between I1 and I5. This is writing to R1. I5 is not reading R1. So by this definition, there is no dependence. In fact, there is no true data dependence. However, we need these dependencies to check or to decide the order of execution. Two independent instructions can be executed in any order without affecting the result of execution. However, dependent instructions cannot be reordered. They need to be executed in the correct order. So let's see to check if there is a dependence between I1 and I5. If they can be executed in any order, that would mean that they are not dependent. They are independent. So can we execute I5 before I1? What would happen if we do that? Okay, so let's try to do that. Let's say we take I5 from here and place it here. Then what would happen to the execution of I6? What's happening right now is I6 is using this address which corresponds to this variable in memory. If we put I5 on top of I1, this R1 would be the value written here. So instead of using address of this variable, we would be using address of this variable in I6, which means wrong execution. This kind of dependencies where there is no data movement between instructions, but you still cannot reorder them because it would lead to wrong execution are called named dependencies or false dependencies. In this particular case, both I1 and I5 are writing their result to same register. And this is why we cannot reorder them. Since this is their output register, they are called output dependence. Now let's talk about this. So now I2 is writing to R2 and R2 is not being read by I5. So there is no true data dependence. Let's check about the output dependence. I2 is writing to R2, I5 is writing to R1. So they are writing different registers. So there is no output dependence. But is there still dependence between these two instructions? Well, let's check. Can we reorder these two instructions? Let's try to put I5 above I2, what would happen? So right now, I2 is reading R1, which corresponds to address of variable A. If we put I5 above I2, it would again be using this R1, but this time it corresponds to variable X. So there will be wrong execution if we reorder these two instructions. Now, this kind of dependencies are called, and this is the same situation here, they are called anti-dependencies. This is, and this happens when you try, when by reordering the instruction, you try to overwrite a register which hasn't yet read by one of the instructions. So this time, again, there is no data movement between instructions. So I2 is not writing to something which is read by I5. However, it's the other way around. If you execute I5 first, I5 will be writing to a register which is later needed by I2. So just to summarize, true data dependencies, there is data movement between instructions. In named dependencies or false dependencies, there is no data movement, but the instructions involved are using the same registers, either at the output or input and output. If they are using the same output register, for example, here it's called output dependence. And if they are using, or if the earlier instruction using an input register which are written by the later instruction, it's called an anti-dependency. Okay, let's see how do these dependencies result in hazards. So here we have three instructions, and this first instruction, what it does is it loads R2 from the address in R0, and it loads R3 from the subsequent address. So let's see how the execution happens in this case. So in the cycle 1, this instruction is fetched. In the next cycle, it is decoded and sub instruction is fetched. In cycle 3, R2 is loaded here. This instruction is decoded and the third instruction is fetched. Now let's see what happens in the fourth cycle. In this cycle, R3 will be loaded. This R3 is needed by sub instruction for its execution. So if we execute sub instruction in this cycle, we have a problem because R3 still doesn't have the correct value. The R3 will be loaded at the end of this cycle. But if we use R3 for the execution in this cycle, we will be using old value of R3, which is wrong. So we cannot execute sub instruction in this cycle. We need to delay its execution to the next cycle. Not only that, the CMP instruction cannot be decoded in this cycle because the hardware unit responsible for decoding is already occupied by the sub instruction. So we need to stop everything behind the execute stage. So execution of this instruction is delayed, decode of the next instruction is delayed, and if we had one more instruction, fetch of that instruction would have also been delayed. So wherever the pipeline stops, all the stages behind that also needs to be stalled. And of course, after delaying the execution of this one, it executes in cycle 5 and the next instruction executes in cycle 6. So the dependencies between first two instruction has caused a bubble in the pipeline, and because of this bubble, we have a reduced clock per instruction and a poor performance. Now let's talk about control dependencies. So here we have a piece of code where this branch instruction may jump to this label or to this instruction. So let's see what happens. So in cycle 1, this branch is fetched. And at this point, we do not even know actually this is a branch instruction because we have just fetched it. We have not decoded it. So we do not know whether it will be taken or not taken. As a result, in the next cycle, we will just fetch the subsequent sequentially next instruction, which is sub instruction from here. And in the next cycle, and in this cycle, the branch instruction will be executed and the other two instructions will be decoded and fetched. At this point, we will know whether this will be taken or not. So what happens if it is taken? If the branch is taken, we need to execute add instruction and note sub and LDR instructions. However, in the pipeline, we have already fetched these two instructions. That means we fetched something wrong. So we need to flush these instructions out of the pipeline. We need to get rid of everything that these instructions has caused in the pipeline. And then start the execution from add instruction. Now what has happened here? Because we didn't know whether this branch will be taken or not, we fetched something wrong. And because of that, we have a penalty of 2 clock cycles, because whatever was done in these 2 clock cycles, clock cycle 2 and 3, was wrong, and we had to undo that and then start doing things from the correct address. Now, this kind of thing results in performance degradation, and how much performance degradation depends upon how many cycles it takes from fetch to the execute of branch instruction. Because when the branch instruction executes, that's when we know what is the correct execution path. In this case, we see that we flushed the amount, we flushed the work done in 2 cycles. So we say our branch penalty is 2 cycles. Okay, let's see if we can avoid these control hazards. Well, the problem is that for some time after fetching the branch, we do not know what the correct execution path is. The one solution to avoid these kind of hazards is that for those cycles, you try to execute instructions which are independent of the branch. So irrespective of whether the branch is taken or not, you can always execute those instructions. For example, in our case, we would need 2 instructions that will always be executed. A question, where can we find such instructions that would be executed irrespective of the branch direction? So if you look at this code, these instructions depend upon whether you want to execute this or not. And this instruction, maybe it's all, whether it will be executed or not depends upon whether there is a branch in this piece of code or not. So any idea where we can find instructions that will always be executed irrespective of whether this branch is taken or not? Well, things that are above this branch. To execute this branch, we need to execute some instructions which are above here before we reach here and diverge the control flow. However, the instructions that are here may be deciding the outcome of this branch. For example, there is a CMP instruction here that sets the flags, and based on those flags, the branch will be decided to be taken or not. So we need to find independent instructions that does not affect the branch direction. And we can move those instructions here, and then they will be always executed. So the advantage is we do not need any hazard detection, and we do not need any flushing if we can do this. The problem is it's really difficult to find such instructions. And this is a very simple pipeline, just 3-stage pipeline. When your pipeline becomes more deeper, then it becomes even more difficult to find instructions because now you need more spaces to fill up. For example, in deeper pipeline, it's very easy that that the branch penalty is 15 and that you need to find 15 independent instructions, and especially considering that basic blocks are only 5 instructions or so. So there is a problem. We cannot, or it's not really easy to find instructions that you can put in branch delay slots. Also, if you cannot find such instructions, you need to put no operations there. And a no operation means you are intentionally inserting a bubble in the pipeline and degrading your performance. Another disadvantage of this approach or branch delay slots is that you are exposing your microarchitecture design to the programmer or compiler, because it's the programmer or the compiler that needs to find these independent instructions. And exposing this microarchitectural design to a programmer or compiler is not a good idea because it might lead to lots of bugs. It also makes the code less portable across different microarchitectures because each microarchitecture can have different number of branch delay slots. An alternate is to use branch predictor. A branch predictor a branch predictor is a device that predicts the direction of branch. It predicts whether the branch is going to be taken or not. If the prediction is right, we are good, we don't need to do anything. But when the prediction is wrong, then we need to flush the pipeline and pay the branch misprediction penalty. However, the branch predictors today are very accurate. Having a branch predictor accuracy of more than 90% is very common. Okay, so we have seen now branch predictor and pipelining that can boost our performance. But these are just very basic techniques. There are lots of other techniques that we can use to boost the performance. Examples include out of order execution. You do not need to execute instructions in which they are placed by the programmer. You can reorder those instructions to minimize the stalls and improve performance. We can also have superscalar processor, which means instead of fetching, decoding, and executing just one instruction per cycle, we can do multiple instructions per cycle. We can fetch multiple instruction, decode multiple instruction, and execute multiple instructions in one cycle. Then we can have multi-threaded processors. Instead of executing just one stream of instructions, we can execute multiple stream of instructions in parallel, and these streams may be part of one application, or they may be part of multiple applications. And there are a bunch of other techniques, for example, prefetching, caching, vector execution that can be very handy in improving the performance. So if you are interested in this kind of stuff, I would highly recommend you to take TDT 40 to 55 computer design and TDT 40 to 60 computer architecture course.